We're going to look at vectors in component form, sometimes called Cartesian form, which is that sort of form there. And we're going to look at magnitude and direction. So we can say if we've got the vector can be expressed like this, as a column vector, sometimes called a storage vector in some contexts, or it can be written in component form. There's each component's there, xi and yj. We can see that they create the resultants, which is vector u. And the magnitude is basically an application of Pythagoras' theorem. So if we have x, I and yj, we apply those to Pythagoras' theorem. The other application is the direction of a vector, which is theta, which is y over x. So it's the same y over x. And so to get theta we need to find the inverse tan, but we must be mindful of the true angle, because this will often give us an acute angle, and an acute angle is not always the one we're after. Another way of formatting the magnitude, you may see it, there's a few other examples, you may see it as such there. Okay, that means magnitude, the bar on each side. Okay, sometimes it's defined as r. In a video further on, we'll talk about trig and polar forms, and they tend to use r instead of the magnitude symbols, but they all mean the same thing. So the magnitude of a vector is always a positive quantity. It's the direction that helps us work out what effect the vector is having, okay, in terms of the where it's going. So if we have some examples here, this first example, we've got 2i plus 2j, and to work out if we call that vector u, the magnitude of u, so you could write that as such, will be 2 squared plus 2 squared, which is the square root of 8, or 2 root 2, because remember, you might know from your work of surds, we can split 8 up into 4 by 2. Square root of 2 is 2. I'll even write that out a bit more for you, like that, in case you've completely forgotten how to use surds. And square root of 4 is 2 times root 2. Okay, that's how you'd find the size or the magnitude of the vector. How do you find that angle? The angle of the vector is anti-clockwise, starting what would be the x-axis, okay, and we're going anti-clockwise, a bit like what you might have seen in a unit circle. And so we know that this vector is going to have a direction between 0 and 90. It's going to be an acute angle. So it's a pretty simple matter. So we've got tan basically, or just go straight to the angle. Theta is inverse tan of y on x, which is the inverse tan of 2 over 2, which is the inverse tan of 1, which is straight 45 degrees. That one's an easy one. What about this next one here? If we've got u is negative 2i plus 2j. Alright, well, the magnitude of u in this case here is negative 2 all squared plus positive 2 all squared, and lo and behold, that comes out as a square root of 8 as well, and that's 2 root 2. So it has the same magnitude, but it has a different effect because it has a different direction. Okay, so for example, if they were forces, it wouldn't have the same effect at all, would they? Now you can already see that the answer for the direction is already there. So what we need to do is find the acute angle first, theta, which will be basically the acute version of that. So here we go. We've got tan, inverse tan, y over x. Now be careful, y is 2, x is negative 2. So it's the inverse tan of negative 1. Now interestingly enough, in a calculator, that will churn out negative 45 degrees. Now be careful. What that means is that the 45 has been going in the anti-clockwise direction. Now this can lead to some confusion, so what you might wish to do instead is, especially this part here, grab it okay, get that there, and basically isolate that, and you've got the vector coming out here. So basically I've redrawn the vector there, the little arrowhead there, and basically if it's negative 2i plus 2j, it'll be 2 in that direction there and 2 there. Just think about it purely as without direction, as a triangle, and we would have, now it's 135 there, but basically it's also a little acute angle there. So the whole thing would be the actual true angle of the vector would be found by whatever the solution to this theta is up here, taken away from 180. So that's what we've got. We'll find the angle we want to find. Okay, so I'm calling that phi, which is the whole angle. Alright, so let's find theta. So that'll be the inverse tan. Theta itself, the little acute angle, will be inverse tan of 2 over 2, which is the inverse tan of 1, which is 45. So an easier understanding of that, that's 45 in there. So 180 take 45 gives the 135. So you write that in there. So 180, so 180, so phi equals 180 take 45, and that's where the 135 degrees comes from. So basically a little tip there, make sure you know what you're finding in terms of angle. It might be okay for you just to turn it into, temporarily, into just purely a triangle trig problem, and then work out where that is in the greater scheme of things, because we sometimes have vectors in all the directions. Sometimes they're down here, sometimes they're there. They're in each of the quadrants, and if you can find an acute angle and then either have it 180 plus the angle in such a case here, or 360 take away, or 180 take away if it's here, you can work out the true angle. Okay, just another little thing too, with ones like this where we have two possible answers, it could be negative 45 or 315. They're both correct, but we tend to use what's called the principal argument, and that means the principal argument is basically we try and keep the stated angle for the vector between negative 180 degrees and positive 180. Alright, that's a convention. And in fact, if I'm going to be super accurate, it's between negative 180 exclusive and 180 degrees inclusive. Okay, so you could see that while it's not wrong, 315 is outside of that, and we could replace it with negative 45. So that's a convention to be aware of.